Right now, light that left a shattered star before Earth even existed is racing toward your eyes at 670 million miles per hour, and that single fact quietly wrecks almost everything you think you know about size. We live inside a comfort zone built from sidewalks and highways, from commutes and flight times, from the deceptive feeling that far is a couple of hours and big is a stadium or a city skyline. We treat miles like meaningful because they are meaningful to legs and car engines. But the universe does not care about legs or car engines. It deals in distances so vast your instincts will try to round them down into something familiar. Tonight, we're going to refuse that instinct. We're going to let the scale of reality hit at full force. Start here. You're standing on a stone sphere screaming around the sun at roughly 67,000 miles per hour, wrapped in an invisible ocean of air, pressing on every inch of you with the weight of an elephant's footprint. You don't notice the pressure because you've never known anything else. You don't notice the speed because there's no wind in space to whistle past your ears. Your senses are brilliant at spotting a tiger in the brush, and terrible at grasping what millions and billions actually mean. Say a million and your brain nods. Say a billion and it nods the same way. But one of those is a dozen days in seconds, the other is more than 3 decades. That gap between what feels big and what is big is the cliff we're about to jump from. Take the thinnest sliver of our world, the atmosphere. If Earth were a basketball, that life-supporting blanket would be thinner than a sheet of paper wrapped around it. Every cloud you've ever watched, every storm, every airplane route, even the summit where Everest knocks the wind out of the strongest lungs, all of it lives in a film so fragile it might as well be breath on glass. Beyond that paper-thin veil lies a black ocean that starts only 62 miles over your head. Stack average people shoulder to shoulder and you'd need tens of thousands of them just to reach the edge of space. The International Space Station, which feels impossibly far away, actually circles closer to your front door than the highway distance between a pair of big coastal cities, yet only a few hundred humans have ever crossed that line. Our greatest leap still barely clears the porch, and still, that porch is lit by a furnace so huge light itself, fastest thing in existence, needs more than 4 seconds to cross its face. Our sun turns 4 million tons of matter into pure energy every second, owns almost everything in our solar system by mass, and still ranks as average in the neighborhood. Average, yet it can burn your eyes from 93 million miles away. Average, yet it makes Earth the kind of place where water runs and lungs work and forests breathe out morning. The scale of that power is easy to admire and hard to internalize. We measure it in sunburns and seasons. The universe measures it in fusions per heartbeat. But here's where your map starts to tear. The places you think are edges, cloud tops, orbital paths, even Pluto's lonely track, aren't edges at all. They're mile markers on a road that refuses to end. Put the entire solar system on a grain of sand, and the next nearest star still sits more than a mile away. Launch a machine at breathtaking speed and let it run for decades. It will just begin to taste interstellar space, and it will still be closer to home than an old family photograph feels in your hands. Between stars there is almost nothing, so little that the best vacuum we can build looks crowded by comparison. Yet that nothing spans gulfs that turn years into inches. Our galaxy adds insult to injury. 200 billion suns, maybe double that, woven into a disk 100,000 light-years wide. A supermassive black hole buried at its heart, quiet and patient, bending time in a neighborhood we can't see because the suburbs where we live are fogged with dust. We ride that disk at 500,000 miles per hour and still need hundreds of millions of years to finish a single lap. Dinosaurs saw a different night sky because the entire sky is moving, and it moves on scales that turn empires into sparks. If that already feels unsteady under your feet, good. The point isn't to whisper trivia, it's to break the habit of shrinking the cosmos down until it fits in your pocket, because what waits ahead makes our proudest numbers look shy. There are stars so swollen they would swallow the inner planets whole. There are dead suns pressed so brutally tight that a spoonful of their matter outweighs mountains. There are collisions that flash brighter than galaxies, and threads of structure so long that even light given 1 billion years tires on the way across. And then there's the invisible majority. Matter we can't see that holds everything together, and an even stranger pressure that pries everything apart, faster and faster, as if emptiness itself had an appetite. So this is your invitation to let go of the comforting ruler. For the next few minutes, we'll move from the world that trained your senses to the one that ignores them. We'll climb past the paper sky, step over the porch light of our star, and keep going until the numbers stop feeling like numbers and start feeling like vertigo. You don't need equations to follow, only curiosity and the willingness to admit your intuition has been lying to you in the kindest possible way. Ready? Take a breath. Look up. That faint glow isn't just a ceiling, it's a time machine, a history book, a lighthouse, and a warning that big is about to be rewritten. And once you see it properly, not with eyes, but with scale, nothing about your place in it will look the same again. Earth feels enormous when you're trapped inside it. To cross a continent by plane takes hours. To walk across a city can take half a day. To drive across the country demands weeks of preparation, gasoline, and a map that feels overwhelming when unfolded on the passenger seat. All of these experiences anchor the idea that our world is a giant, a vast landscape so massive it defines what big means. But the truth is that Earth is a very small piece of a puzzle that grows stranger with every layer. What feels infinite to us is fragile, fleeting, and almost invisible when set against even the next step outward in scale. Start with the ground beneath your feet. It feels permanent, solid, safe. Yet Earth is little more than a thin crust riding on molten rock, with a radius of just under 4,000 miles. To your senses, that sounds limitless, because you'll never walk it, but compare it to the sun, which is over 100 times wider, and Earth shrinks to the scale of a tiny marble beside a glowing beach ball. Even before we leave our own neighborhood, the illusion of size begins to collapse. The ground that lays unshakable is only a speck of dust orbiting a furnace. Now look up. The atmosphere you trust every moment of your life is not endless sky. It's an ocean of air pressing on your body with a force of 14 pounds for every square inch of skin. That sounds crushing until you realize you've been adapted to it since birth. The truth is the atmosphere is thinner than you imagine. So thin, in fact, that if you shrank Earth to the size of a basketball, the entire atmosphere would be no thicker than a single sheet of paper wrapped around it. Every cloud, every bird, every drop of rain that ever fell has existed inside that flimsy layer. Beyond it lies space, silent and airless, just 62 miles up, a distance you could drive in an hour on the freeway. 62 miles is less than the space between two nearby cities, but that is the height at which the sky ends. The moon proves just how deceptive distance can be. At night, you can block it with a fingertip. Your mind tells you it is small and close. In truth, it hangs 240,000 miles away. That is 10 times the circumference of Earth. Light, the fastest thing we know, takes more than a second to cover the gap. For a rocket, it's a 3-day trip, a journey that only a few dozen humans have ever made. The moon looks near enough to touch, but it is farther away than your instincts can imagine. If Earth and Moon were shrunk to basketballs, you'd need to place them nearly 30 feet apart to get the scale right. That empty gap is the real story, and our eyes lie to us every time we look up. Numbers, of course, don't help much either. 1 million and 1 billion sound similar to the human ear. Both just mean a lot, but the gap is enormous. 1 million seconds is about 12 days. 1 billion seconds is 32 years. That's the kind of difference your brain smooths over, and it's why cosmic distances feel meaningless when read out loud. To grasp them, you need metaphors. The grain of sand, the mile-wide desert, the paper-thin veil of air. Without those, the numbers collapse into a blur. So here is the first lesson of scale. Earth is only huge if you never leave it. It's massive if your world is flights and highways. But compared to what surrounds it, Earth is an invisible speck, an island smaller than dust in an endless ocean. Its air, its seas, even the moon that circles it, are fragile pieces of a system so delicate it can be swallowed by the next level of cosmic comparison. And we haven't even stepped beyond the backyard yet. The moment you do, the ground that feels infinite under your feet becomes a rounding error in the universe's math. This is where the illusion of size begins to break, and where the real journey starts. Step just a little beyond the atmosphere, and the scale you thought you understood begins to shatter completely. Space doesn't start at some unreachable distance. It begins a mere 62 miles above your head, at a boundary known as the Kármán line. 62 miles is nothing on Earth. People drive farther than that for a weekend getaway, and commercial planes often cover that distance in less than 10 minutes. Yet at that invisible line, blue fades to black, the air becomes too thin to breathe, and the protective ocean of atmosphere you rely on every moment vanishes beneath you. Imagine stacking average-sized humans, one on top of the other, shoulder to shoulder, until you reach that edge. You'd need nearly 60,000 of them just to build a human ladder into space. That short drive on Earth is a vertical wall into a void. Your lungs cannot survive. Even Mount Everest, the tallest mountain on Earth, doesn't come close. Climbers risk their lives at 29,000 feet, where the oxygen is already so thin that every breath feels like drowning. They call that region the death zone. But the peak of Everest is barely a third of the way to the height where space officially begins. To actually reach the Kármán line, you'd need to stack 11 Everests on top of one another. Think about that. Our planet's mightiest mountain wouldn't even get you 1/10 of the way to true space. Now think about the International Space Station, orbiting about 250 miles above Earth's surface. To your imagination, that feels like an unfathomable distance. Yet in practical terms, it's closer than a 3-hour car drive at highway speeds. New York to Washington, D.C. is farther than the height astronauts orbit. And yet, for humanity, that orbit remains one of our greatest achievements, a fragile outpost in a realm that begins just above our atmosphere's paper-thin ceiling. The strangest part? Astronauts aboard the station aren't weightless because there's no gravity. In fact, Earth's gravity up there is still nearly 90% as strong as it is on the ground. They float because they're falling endlessly around the curve of the planet at over 17,000 miles per hour. Their orbit is a perfect balance between speed and gravity. Fall fast enough and the ground curves away beneath you. That's the delicate trick of orbit. It looks serene on camera, but it's a knife-edge dance at blistering speed, where a small miscalculation could mean tumbling back into the atmosphere or flinging into deeper space. Fewer than 700 people in the history of humanity have ever crossed that line into orbit. Billions of us live and die under the sky, but only a handful have felt the strangeness of seeing the whole planet beneath their feet at once. From that height, Earth doesn't feel endless. It feels fragile. You can see the paper-thin line of atmosphere hugging the planet like a faint blue halo. You realize the only thing separating life from vacuum is a layer so thin it looks like breath on glass. Even the moon, our closest neighbor, remains bound inside Earth's gravitational influence. It's only 3 days away by rocket, which is close by cosmic standards, yet it still sits 10 Earths apart in distance. That familiar silver disk that looks small enough to touch is a world 1/4 Earth size, hanging hundreds of thousands of miles away in a gulf of black nothingness. And so far, only a few dozen humans have ever walked its surface. This is where our understanding of distance begins to fall apart. The International Space Station is closer to you than a road trip, yet feels impossibly far. The moon is just 3 days away, yet feels impossibly near. Our brains are built to measure steps and car rides, not to juggle miles stacked by the hundreds of thousands. And already, the gaps are widening beyond anything that makes sense. From this point onward, the rulers we've always trusted begin to fail us, because the next step out, the sun, our very own star, dwarfs everything we've seen so far. 8 minutes and 20 seconds, that's how long it takes for sunlight to reach your face. In those 8 minutes, photons leave the surface of our star, travel 93 million miles of vacuum, and finally warm the ground beneath your feet. To you, the sun is a glowing disk you can block with your hand. To physics, it's a raging nuclear furnace, so colossal that light itself, the fastest thing in existence, needs more than 4 seconds just to cross its surface from one edge to the other. Think about that. Light can circle the entire Earth 7 times in a single second, yet it struggles to clear the sun's diameter in less than 5. That is the kind of scale we're dealing with. The sun contains 99.86% of all the mass in our solar system. Everything else, planets, moons, asteroids, comets, accounts for less than 1/5 of 1%. If our solar system were a giant pizza, the sun would be the whole pie, with the planets as a few crumbs scattered on the edge of the plate. Jupiter, the largest planet, is a massive ball of gas over 1,000 times bigger than Earth. But even Jupiter looks like a toy next to the sun. You could line up 100 Earths across the sun's face and still not cover it. In terms of sheer size, the sun dwarfs everything you've ever thought of as large. But it isn't just the size that should shatter your sense of scale. It's the power. Every single second, the sun converts about 4 million tons of its own matter into pure energy through nuclear fusion. That energy radiates outward in all directions, sustaining life on Earth, while blasting planets like Mercury with heat so extreme their surfaces bake during the day and freeze into brutal cold at night. The process is mindless, inevitable, and unstoppable. It has been happening for over 4.5 billion years and will continue for at least another 5 billion. To put that in perspective, the sun produces enough energy in 1 second to power human civilization for hundreds of thousands of years. And here's the part that really scrambles your perspective. The sun is nothing special. Astronomers classify it as a yellow dwarf, an average star in every respect. In our galaxy, there are stars so massive and bright that they make the sun look like a faint candle. Some burn through their fuel so quickly they live only a few million years instead of billions. Others swell into red supergiants so vast they would engulf Earth and reach out past Jupiter if they replaced our sun. Compared to those giants, our star is humble, ordinary, forgettable. The only reason it feels extraordinary is because it is close, because we depend on it completely, because without its warmth, Earth would be a frozen rock drifting through space. But even its nearness deceives you. The sun is 93 million miles away. So far that if you could drive a car straight into the void at highway speeds, the trip would take over 170 years without a single rest stop from Earth. That distance makes the sun appear small enough to blind you in an instant, yet its actual presence is overwhelming. It dominates every aspect of life, not just with its heat and light, but with its gravity. The planets do not circle it casually. They are held in its grip, each one trapped in an endless fall, orbiting because of the sun's sheer mass. Every comet, every asteroid, every speck of dust in the solar system dances to the sun's pull. And yet, this average yellow dwarf is not eternal. In 5 billion years, the sun will swell into a red giant, engulfing Mercury and Venus, maybe Earth, before shedding its outer layers and shrinking into a white dwarf no larger than our planet. It will die, not with a bang, but with a slow fade, leaving behind the elements that built the very ground you walk on. In fact, the carbon in your body and the oxygen you breathe were forged in ancient stars before the sun was even born. The sun is our life source, but it's also part of a cycle much bigger than itself. This is the paradox of the sun, at once ordinary and extraordinary, average and overwhelming. From your perspective, it is the center of everything. But in reality, it's just one star among hundreds of billions, humming quietly in a corner of the Milky Way. And if this average star can already swallow 1 million Earths, turn mass into energy with terrifying efficiency, and dominate our entire solar system, then what happens when we step beyond it? What happens when we leave the sun behind and look toward the vastness between stars? That is where the real scale begins to unfold. Beyond the sun lies a darkness that stretches farther than the imagination can comfortably hold. Most people picture the solar system ending at Pluto, a lonely frozen world on the edge of sunlight. But Pluto is no edge. It's barely a marker along the way. Beyond it lies the Kuiper Belt, a ring of icy remnants that extends billions of miles further. And even that is just the inner boundary of something much greater, the Oort cloud, a vast spherical shell of comets that may stretch halfway to the nearest star. The Oort cloud is so distant that a spacecraft launched today at record speed would take thousands of years just to reach its outer regions. To put this in perspective, if the solar system were shrunk down to the size of a grain of sand, the next nearest star would still be a mile away. That is how empty the spaces between stars really are. Voyager 1, the farthest human-made object, has been racing outward since 1977 at 38,000 miles per hour. For nearly half a century, it has never slowed, never rested, always pushing outward. And yet after all this time, it has only just left the sun's protective bubble of charged particles. It hasn't come close to reaching another star. At its current speed, it will need about 40,000 years to pass within sight of Proxima Centauri, our closest stellar neighbor. 40,000 years, that's longer than the span of recorded human history, longer than civilizations have existed. By the time Voyager brushes against another system, everything familiar to us will be gone, and the night sky itself will have changed beyond recognition.
And what fills the void between stars? Almost nothing. In the emptiest reaches of interstellar space, a cubic foot may contain a single lonely hydrogen atom. That's it. Compare that to Earth's atmosphere, which holds trillions upon trillions of molecules in the same space, and you begin to see how alien true emptiness is. Even the most advanced vacuums humans can build in laboratories still contain millions of atoms per cubic foot, far denser than interstellar space. Out there, nothingness isn't a metaphor, it's reality.
But emptiness doesn't mean stillness. Our sun is one of hundreds of billions of stars bound together in the Milky Way galaxy. Picture a glowing city of light stretching 100,000 light years across, a disk so wide that even at light speed, it would take 100,000 years to travel from one side to the other. Every star you've ever seen with your naked eye is part of this one galaxy, and most of the stars you will never see are hidden behind clouds of dust that block the center from view. Our solar system sits about 26,000 light-years from the galactic core, drifting in a minor spiral arm, and like every other star, we orbit the center. One lap around the galaxy takes about 20-30 million years. The last time our sun was in its current position, dinosaurs were just beginning to roam Earth. At the heart of the Milky Way lurks something even stranger, a supermassive black hole called Sagittarius S, with the mass of 4 million suns crushed into a region smaller than Mercury's orbit. Its presence bends the paths of nearby stars, whipping them around at incredible speeds, and its gravity distorts time itself. From our distance, the black hole is quiet, invisible behind clouds of dust. But if those clouds vanished, the galactic center would blaze in our sky brighter than the full moon. Billions of stars packed so closely together would turn the night into a glowing river of light. Instead, we live in the suburbs of the galaxy, where stars are sparse and the skies are darker. Every star you see overhead is just a tiny spark in this vast system, one city of light among countless others. And even though the Milky Way feels like everything, it is just one galaxy among billions, drifting through a universe stitched together by threads of matter. Between its stars lies the truest emptiness you can imagine, but on the largest scale, it all connects into something even more staggering. Beyond the galaxy's rim, the web of the cosmos begins to appear. And once you see that web, you realize the Milky Way itself, home to all of human history, is nothing more than a single glowing bead in a structure so vast it defies reason. The Milky Way is home, but calling it home can be misleading. Home suggests something familiar, something within reach, something you could, at least in theory, cross in a lifetime. The galaxy is nothing of the sort. It is a vast, sprawling metropolis of stars, stretching 100,000 light-years across, so enormous that even light itself, the ultimate speed limit, needs 100 millennia just to move from one side to the other. And light is not the only thing in motion. Every star, including our own sun, is caught in a gravitational whirlpool around the galactic center. Right now, our solar system is orbiting at an astonishing 515,000 miles per hour, fast enough to circle Earth 20 times in a single day. Yet we still need 20-30 million years to complete just one lap. When the sun last passed this position in the galaxy, dinosaurs had only begun to dominate Earth. That's how long a galactic year lasts. Civilizations rise and fall, species appear and vanish, yet the galaxy keeps turning, indifferent to the stories written on one small planet. And the Milky Way isn't a quiet city, it is alive with drama. Stars are born in clouds of gas, so vast they could swallow thousands of solar systems. In these stellar nurseries, gravity compresses hydrogen until nuclear fires ignite, birthing new suns that will shine for millions or billions of years. Elsewhere, old stars are dying. Some fade gently into white dwarfs, cooling embers that will glow for trillions of years. Others go out violently, detonating as supernovae that briefly outshine the entire galaxy before collapsing into neutron stars or black holes. Each death seeds the surrounding space with heavy elements: carbon, oxygen, iron, gold, the ingredients for planets and for life itself. You and I exist because ancient stars exploded long before our sun was born, scattering the raw material that would become oceans, forests, and blood. But the Milky Way also hides monsters. At its heart lies Sagittarius A, the supermassive black hole 4 million times more massive than the sun. Stars whip around it at breakneck speeds, completing orbits in just 16 years. Its gravity is so intense that time slows near its edge, and light itself struggles to escape. For the most part, this beast sleeps quietly, feeding only on the occasional gas cloud or stray star that wanders too close. But when it feasts, it can unleash jets of energy powerful enough to light up the galaxy. And it isn't alone. Scattered throughout the Milky Way are smaller black holes, the corpses of massive stars. Some lurk unseen, invisible, except for the way they tug on nearby stars. Others blaze brightly as they consume matter from companion stars, radiating X-rays across the cosmos. Our galaxy is not even static in shape. It is devouring its neighbors right now. Smaller galaxies are being stretched into streams of stars, pulled apart by the Milky Way's gravity, their remnants wrapping around us like ghostly ribbons. In about 4 billion years, the Milky Way will collide with Andromeda, our nearest large galactic neighbor. The two spirals will merge into a giant elliptical galaxy, reshaping the night sky forever. Stars will rarely collide. Space is too empty, but the gravitational chaos will fling suns into new orbits and ignite bursts of star formation. To future civilizations, the skies will blaze with unfamiliar patterns, their constellations erased and rewritten by the merger. Think of what this means. Every star you see in the night sky is only a local spark. There are hundreds of billions more in our galaxy alone, each with the potential for planets, each with the possibility of life. If you tried to count them one per second, it would take you over 12,000 years to finish. And yet the Milky Way is just one galaxy in a universe of billions. Seen from afar, it would look like a tiny spiral of light, one pinprick in a cosmic ocean. The entire galaxy, with its black holes, nebulae, suns, and history, could fit into a corner of a larger map without standing out. So when you step outside at night and look up, remember that you're not just seeing stars, you're seeing the edge of an empire too vast to comprehend. You're looking into a system that is ancient, violent, and alive with motion. And as immense as it feels, the Milky Way is small. Beyond it lies an expanse filled with galaxies by the 100 billion, stitched together into structures so large they make our home galaxy look like a grain of sand. That is where the true immensity begins to reveal itself. Among the billions of stars in the Milky Way, not all live quiet, predictable lives. Some are born heavy and furious, burning their fuel so quickly that they collapse in spectacular deaths after only a few million years. What they leave behind are corpses unlike anything the human mind evolved to comprehend. These remnants are neutron stars, objects so dense and strange that the very idea of solid or heavy becomes meaningless. A teaspoon of neutron star matter would weigh billions of tons more than every skyscraper on Earth combined. Imagine holding something in your hand that contains the weight of a mountain. That is what density means on these scales. Neutron stars are created when massive stars explode as supernovae. During the collapse, the core is crushed so brutally that protons and electrons merge into neutrons. The result is a sphere barely 12 miles across, about the size of a city, yet with more mass than our sun. Gravity on the surface is 200 billion times stronger than Earth's. If you could stand there, which you couldn't, because you'd be obliterated instantly, you would weigh as much as Mount Everest. Even light struggles to climb out of their gravity wells, stretching redder and dimmer as it escapes. Some neutron stars spin with impossible speed. The fastest pulsars rotate hundreds of times per second, whipping their equators around at nearly a quarter the speed of light. They emit beams of radiation from their magnetic poles, sweeping across space like lighthouses. From Earth, we detect these flashes as perfectly timed pulses, accurate to the millisecond. In fact, Pulsars keep time more precisely than the best atomic clocks ever built by humans. These cosmic clocks are so stable that astronomers use them to detect ripples in space-time itself, gravitational waves from colliding giants millions of light years away. Then there are magnetars, the most magnetic objects in the universe. Their magnetic fields are 1,000 trillion times stronger than Earth's. If a magnetar were as close as the moon, its field would erase every credit card on Earth and shred the electrons in your body. These monsters occasionally release bursts of energy so violent they can outshine entire galaxies for a brief moment. And yet, they are nothing more than stellar corpses, remnants of stars that once burned brightly and died young. But neutron stars don't exist in isolation. Some live in binary systems, stealing matter from companion stars, gas funnels onto the neutron star, heating to millions of degrees and releasing X-ray bursts more powerful than anything a human imagination could conjure. In some cases, two neutron stars orbit each other in a deadly dance, spiraling closer over millions of years as they radiate gravitational waves. When they finally collide, the explosion is so powerful it forges gold, platinum, and uranium in an instant, elements that later become wedding rings, electronics, and nuclear fuel. Every piece of gold you've ever seen was born in the heart of a neutron star collision billions of years ago. Neutron stars are laboratories for physics we cannot reproduce on Earth. Their cores may hide exotic states of matter where neutrons dissolve into quarks or stranger particles we have yet to discover. They stretch the laws of physics to their limits, bending time, warping space, and defying every intuition evolution has given us. On Earth, we measure weight in pounds or kilograms. On a neutron star, a marshmallow dropped from a few feet would strike with the energy of 1,000 hydrogen bombs. The surface is so smooth that mountains cannot rise more than a fraction of an inch before being crushed flat by gravity. These objects are both terrifying and beautiful, reminders that the universe plays by rules far beyond human comfort. They show us that death in the cosmos is not an end, but a transformation, a rebirth into forms, stranger and more extreme than anything alive. And yet, as mind-breaking as neutron stars are, they are still not the final word in cosmic violence, because beyond them lie black holes and quasars, objects that bend reality itself into shapes we struggle to even describe. Compared to those, neutron stars are only the beginning of the universe's darker story. If neutron stars are the strange corpses of ordinary giants, then quasars are the blazing hearts of galaxies gone wild. To understand a quasar, picture a black hole not as the silent predator you might imagine, but as a voracious engine of light. At the centers of galaxies lie supermassive black holes, millions or even billions of times more massive than our sun. Alone, they are invisible, swallowing light and vanishing into darkness. But feed them, and they transform into the most luminous objects in the universe. Gas, dust, and even entire stars spiral inward, forming an accretion disk that spins faster and faster as it nears the event horizon. Friction and magnetic fields superheat this material to billions of degrees, hotter than the core of any star, until it blazes brighter than 1 trillion suns. That spectacle is what we call a quasar. Quasars are paradoxes. They are powered by darkness, yet shine more fiercely than anything else we know. A single quasar can outshine all the stars of its host galaxy combined, visible across billions of light years. The most powerful quasars beam light that left them when the universe was young, just a few 100 million years after the Big Bang, yet we still detect that light today. They are cosmic lighthouses from the dawn of time, reminders that galaxies were already growing monsters in their hearts before Earth even existed. The power of a quasar isn't just in its glow. Many of them fire out jets of plasma that stretch for millions of light years, launched at nearly the speed of light along magnetic field lines. These jets can pierce through the galaxy and beyond, spreading energy and matter into intergalactic space. Imagine a beam of energy so steady it remains focused across distances larger than clusters of galaxies. These jets sculpt their environments, trigger new star formation in some regions, and choke it off in others. In many ways, quasars are both creators and destroyers, shaping the growth of galaxies themselves. And the scale is almost cruel to the imagination. The Sun, our mighty star, converts about 4 million tons of matter into energy every second. Impressive, until you realize a quasar can release thousands of times more energy in the same instant. While stars are fusion reactors, black holes are gravity engines, converting mass into energy with far greater efficiency. A star might turn less than 1% of its mass into usable energy. A black hole can unleash 30% or more. It is the ultimate power plant, and the fuel is everything that dares to come too close. The most distant quasars push our telescopes to their limits. Their light has traveled more than 13 billion years to reach us, meaning we see them not as they are, but as they were when the universe was less than 1 billion years old. To witness a quasar is to look back in time, almost to the beginning, to see galaxies in their violent youth. These early quasars pose deep mysteries. How could black holes have grown so enormous, so quickly, when the universe was still young? Their existence suggests that either the first stars collapsed into black holes far larger than we thought possible, or that these ancient black holes consumed matter at rates we once believed impossible. For astronomers, quasars are more than dazzling curiosities. They are tools. Their light acts like a flashlight, shining through the universe, carrying with it imprints of everything it passed through. As quasar light travels billions of years, it filters through clouds of hydrogen, gas, and dust, leaving subtle fingerprints in its spectrum. By studying these fingerprints, scientists can map the large-scale structure of the cosmos, the filaments and voids that form the cosmic web. In this way, quasars illuminate not just the distant past, but the invisible scaffolding of the universe itself. Blazars, a special kind of quasar, are even more extreme. These are quasars with jets pointed almost directly at Earth, and they appear to flicker and flare unpredictably. When they erupt, they can temporarily become the brightest gamma-ray sources in the sky, outshining everything else. To us, they seem violent and unstable, but in reality, we are simply standing in the path of a jet that would look calmer from another angle. Their unpredictable brilliance makes them some of the most dangerous and fascinating objects we can observe. Yet, for all their violence, quasars are temporary. They burn for a cosmic moment, millions of years at most, before their fuel runs out. Once the gas around them is consumed or blown away, the quasar fades, leaving behind a quiet galaxy with a sleeping black hole at its core. Our own Milky Way likely hosted a quasar phase billions of years ago, blazing brighter than anything in its surroundings. Today, Sagittarius AX rests, consuming little more than a trickle of gas, but it could awaken again if fed a fresh supply of matter. Quasars remind us that galaxies themselves are not peaceful islands, but evolving, dynamic systems with violent hearts. They bridge the gap between the deathly silence of black holes and the blinding brightness of stars, and they hint at a deeper truth. Even the most powerful engines of light are just one piece of something larger. Because when you step back and see where quasars live, you begin to notice the universe is not a random scattering of galaxies. It is woven into patterns, threads, and walls on scales, so enormous they break every frame of reference we have. That tapestry, the cosmic web, is the next layer of reality, and it makes even quasars look small. From far enough away, the universe stops looking like a scattering of stars and galaxies and starts looking like a pattern, an intricate, three-dimensional web stretched across unimaginable distances. This is the cosmic web, the largest structure in existence, and it is the framework upon which the universe itself is built. Imagine soap bubbles clustering together in a sink. The edges of those bubbles meet at thin walls, and in between them lie empty voids. Now stretch that analogy to scales of hundreds of millions of light years, and you yearn to glimpse the true architecture of the cosmos. Galaxies are not sprinkled randomly through space. They trace out vast filaments, thread-like structures made of both dark matter and gas that connect galaxy clusters like beads on a string. These filaments are unimaginably long, often hundreds of millions of light years in length, yet astonishingly thin compared to their extent, just a few million light years across. To call them threads is almost literal. Their proportions are more extreme than a human hair compared to its length. Along these threads, matter flows slowly inward, pulled by gravity, feeding galaxy clusters that act as the dense nodes of this universal network. Between the filaments lie voids, the largest empty regions in the universe. These voids can span hundreds of millions of light years and contain almost no galaxies at all. The largest known, the Botas void, is 330 million light-years wide. If the Milky Way were placed in its center, we wouldn't have discovered other galaxies until we invented modern telescopes, because nothing bright enough would lie close enough to see with the naked eye. Standing there would feel like being adrift in an ocean with no shore in sight. The cosmic web is more than just a striking arrangement. It is the skeleton of the universe. Dark matter, which outweighs visible matter 5-to-1, forms the invisible scaffolding. Ordinary matter, gas, dust, stars, planets, simply falls into the gravitational wells carved out by this hidden framework. Without dark matter, galaxies would never have formed. The universe would still be a smooth fog of hydrogen and helium. Instead, the web provided the gravitational highways along which material could clump, collapse, ignite, and evolve into the stars and galaxies we see today. Superclusters mark the nodes where filaments intersect. These vast regions can contain thousands of galaxies bound together by gravity. Our own Milky Way belongs to the local group, which itself is part of the Laniakea supercluster, a region stretching over 500 million light-years. But even Laniakea is only a piece of something greater. The Sloan Great Wall, discovered in the 1980s, is a chain of galaxies extending 1.4 billion light-years. More recently, astronomers have mapped the Hercules Corona Borealis Great Wall, a staggering structure 10 billion light-years across, so large that it challenges our understanding of how such structures could form in the time since the Big Bang. And yet, even these walls are not solid. They are made of countless galaxies separated by vast gulfs of emptiness, all arranged into a thin, almost foamy pattern. To scale it properly in your mind, shrink the Milky Way to the size of a single grain of sand. Place billions of these grains along threads, stretching across the length of continents, with deserts of nothing in between. That is the cosmic web. What makes this structure even more extraordinary is that it carries the imprint of the universe's earliest moments. The faint ripples seen in the cosmic microwave background, tiny fluctuations in temperature, 1 part in 100,000, were the seeds of this web. Over billions of years, gravity amplified them, pulling matter into the ridges while leaving valleys of emptiness behind. What you see when you map galaxies on the larger scale is the fossilized fingerprint of the infant universe, and we are still only scratching the surface of what these patterns mean. The cosmic web challenges our ideas of size, but it also raises deep questions. If structures this vast exist, how far do they extend? Are we seeing only a small piece of an even larger pattern, one that stretches beyond the observable universe? And what role does dark energy play in shaping or stretching these filaments as it accelerates the expansion of space itself? The cosmic web makes even quasars look like sparks in a bonfire. It takes our Milky Way, a galaxy we consider impossibly grand, and reduces it to a single bead strung along a thread that itself is only part of a far greater weave. The truth is humbling. We do not live in a galaxy so much as we live in a node of an infinite tapestry, connected to other galaxies by invisible bridges of matter and energy. And yet even this grand design may be just a backdrop, because behind it lies a deeper mystery still, the force that is not just shaping the web but tearing the universe apart faster and faster with each passing billion years. That mystery is dark energy, and it represents the next level of scale, stranger and more elusive than anything we can see. Dark matter may build the skeleton of the universe, but it is not the whole story. The true ruler of cosmic fate is something stranger, more elusive, and even harder to grasp. Dark energy. While dark matter holds galaxies and filaments together, dark energy is pushing everything apart. It is not an object, not a particle, not something you can point to in the night sky. It is a property of space itself, an invisible pressure woven into the very fabric of reality. And though you cannot see it, it makes up nearly 70% of the entire universe. That means most of what exists isn't stars, planets, or even dark matter. It is this mysterious force that defies our deepest understanding of physics. To appreciate just how bizarre dark energy is, rewind the universe back about 9 billion years. At that time, cosmic expansion, the stretching of space itself, was slowing down. Gravity, the universal glue, was winning. Galaxies were pulling on each other, and the growth of the universe was decelerating. But then something unexpected happened. Roughly 5 billion years ago, that trend reversed. Expansion didn't just continue, it began to speed up. Galaxies started racing away from each other faster and faster, as though some hidden hand had shifted the gears of reality into overdrive. That invisible acceleration is what we call dark energy. On small scales, like solar systems or galaxies, you don't notice it. Gravity is strong enough there to keep things bound. Earth doesn't drift away from the sun, and stars don't get pulled out of the Milky Way. But on the largest scales, the vast gulfs between galaxy clusters, dark energy dominates. Imagine a tug of war where one team slowly gains ground without anyone noticing, until suddenly the rope begins to slide uncontrollably. That is the moment the universe entered 5 billion years ago, and it has been accelerating ever since. The consequences are staggering. Right now, we can see galaxies up to about 46 billion light-years away, limited by the age of the universe and the speed of light. But because space itself is expanding faster and faster, galaxies beyond a certain distance are moving away from us faster than light itself. They are not breaking the cosmic speed limit. Rather, the space between us and them is stretching too quickly for light to ever bridge the gap. That means entire galaxies, entire clusters of galaxies, are disappearing from view forever. Every year that passes, more of the universe slips beyond our reach, vanishing not because it is gone, but because the light it emits will never catch up to us. If this continues indefinitely, the far future of the universe looks lonely. Our local group of galaxies, the Milky Way, Andromeda, and a few dozen smaller companions, will remain gravitationally bound. In about 4 billion years, the Milky Way and Andromeda will merge into a giant elliptical galaxy. But beyond that local island, everything else will fade away. The Virgo cluster, the Coma cluster, all the galaxies we can see in the night sky today, They will slip past the horizon, leaving our descendants marooned in a cosmic desert, with no evidence of the wider universe. Billions of years from now, future astronomers may look up and see only their own galaxy, never knowing that billions of others once shone nearby. What exactly is dark energy? The most straightforward explanation is that it is the energy of empty space itself, a cosmological constant, first suggested by Einstein, then discarded, then rediscovered when the acceleration was detected in the 1990s. But this answer only deepens the puzzle. Quantum physics predicts that empty space should be filled with energy. But the amount it predicts is larger than observations by a factor of 10. That's not just a mistake, it's the largest mismatch between theory and observation in all of science. Other ideas suggest that dark energy could be something dynamic, a new field called quintessence that evolves over time. In this picture, the acceleration might not be constant. It could strengthen or weaken depending on how the field changes. If it grows stronger, the universe may face the Big Rip, where even galaxies, stars, and atoms are torn apart as space itself expands faster than matter can hold together. If it weakens, perhaps expansion will slow again, leading to a big crunch where everything collapses back into a final inferno. Right now, we don't know which, if any of these futures awaits us. What we do know is that dark energy is already rewriting the story of the cosmos. It ensures that most galaxies will never be touched, never be visited, never even be seen after a certain time. It sets the boundary of what we can know, shrinking the cosmic horizon even as our telescopes improve. And it leaves us with a profound paradox. The universe is dominated by something we cannot see, cannot measure directly, and cannot explain, yet its fingerprints are everywhere in the sky. Dark energy turns the cosmos into a place where emptiness itself is alive, where the vacuum has weight, and where the future of everything depends on a force we barely understand. It shows us that the universe is not just vast, it is dynamic, evolving, and ultimately temporary in its forms. And it raises one final unsettling question. If most of the universe is invisible and incomprehensible, how much of reality are we truly missing? To search for that answer, we must look deeper into time itself, toward the ancient light still echoing across the sky from the moment the cosmos began. That light, the cosmic microwave background, is our last and oldest clue, and it will take us to the edge of what we can ever know. Long before galaxies took shape, before stars ignited and planets formed, the universe was nothing like the place you see today. It was dense, hot, and blinding, filled with a plasma of particles and light locked together in a chaotic soup. Photons, the particles of light, couldn't travel freely. They bounced endlessly from one electron to another like prisoners in a crowded cell. Space itself was glowing but opaque. For nearly 400,000 years after the Big Bang, no light could escape across the cosmos. Then, in an instant of cosmic history, everything changed. The universe cooled enough for electrons to bind with protons, forming the first stable atoms of hydrogen. Suddenly, light was free to travel, stretching outward in all directions, carrying with it the imprint of the newborn universe. That light is still here today, filling every inch of space as a faint glow we call the cosmic microwave background, the oldest light we can ever see. At first glance, it doesn't look like much. Detect it with a simple radio receiver, and it registers as a gentle hiss, quieter than static on an old television. But hidden in that faint background are the fingerprints of creation itself. When satellites like COBE, WMAP mapped it in detail, they revealed a nearly uniform glow, with tiny ripples in temperature no greater than a few millionths of a degree. Those ripples, as subtle as they are, tell the story of everything. They are the frozen echoes of quantum fluctuations stretched to cosmic scales by inflation, the tiny irregularities that grew into galaxies, stars, and eventually us. Without those small differences, matter would have remained evenly spread, and the universe would be nothing but a thin, lifeless fog. The cosmic microwave background, CMB, is often described as a baby picture of the universe, taken when it was just 380,000 years old. In human terms, that's less than a day after birth compared to the span of a lifetime. Looking at it is like seeing an infant photograph of existence itself, and the details in that picture reveal more than just a snapshot. They reveal the universe's age, composition, and shape. By measuring the patterns of the CMB, scientists have determined that the universe is 13.8 billion years old, that it is made of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy, and that space itself is astonishingly flat, stretching out like an endless sheet. But the CMB isn't just a relic, it's also a boundary. It marks the farthest we can see with light, the limit of the observable universe. Beyond it lies a time when the cosmos was still opaque, when light itself could not travel. That means no matter how powerful our telescopes become, we will never see past this wall with electromagnetic radiation. It is a horizon written into the physics of existence. To glimpse further back, scientists must look for different messengers, gravitational waves or neutrinos, that may have carried information from before this last scattering of light. For now, the CMB is our ultimate curtain, and yet, even this ancient glow carries mysteries. There are strange anomalies, cold spots, larger than expected, alignments of ripples that shouldn't exist if the universe is truly random and uniform. Some scientists suggest these could be evidence of physics beyond our current models, perhaps even hints of other universes brushing against our own. Others argue they are statistical flukes, the kind of odd patterns that appear naturally in any large data set. Either way, they remind us that the universe still hides secrets even in its most ancient light. Think about what this means. When you look at the CMB, you are seeing the edge of time, light that began its journey almost 14 billion years ago and only just reached us. Every cubic centimeter of space around you is filled with hundreds of these photons, stretched by expansion into microwaves so long that your eyes cannot see them. They pass through you constantly, silent messengers from the dawn of everything. The very atoms in your body were once bathed in this glow, long before Earth existed, long before the sun was born. The cosmic microwave background is both an end and a beginning. It is the oldest light we can observe, the first true picture of the universe, but it is also a reminder of what lies beyond, of regions and eras forever hidden from view. Beyond the CMB, we enter a realm we can never directly see, a time when the universe was younger than a heartbeat, when space expanded faster than light itself, when the seeds of all structure were planted in the quantum foam. That is the true mystery of origins, and it lies forever just beyond the edge of what light allows us to know.